may seem like a simple question, but knowing the answer will provide us with a much more complete understanding of how the universe works. To get these answers, we must go back to the very beginning, to less than 1/1000th of a second after the Big Bang. In the first few moments after the Big Bang, the four forces of nature began to split apart, and huge inflationary expansion took place, increasing the size of the universe to unimaginable proportions. In these extremely hot conditions, the fundamental particles began to form and whiz around at the speed of light. Only a small fraction of a second later, some of these particles acquired their mass and allowed
At the world's largest particle accelerator at CERN in Geneva, Switzerland. Deep underground.
Insignificant though this bottle of compressed hydrogen gas looks, it marks the beginning of the world's largest and most powerful particle accelerator chain, culminating in CERN's spectacular Large Hadron Collider. Hydrogen atoms from this gas cylinder are fed at a precisely controlled rate into the source chamber of a linear accelerator, CERN's LINAC-2, where their electrons are stripped off to leave hydrogen nuclei. These are protons and have a positive charge, enabling them to be accelerated by an electric field. Their journey to eventually take part in ultra-high energy collisions similar to those following the Big Bang can now begin. This initial acceleration has caused LINAC-2 to be likened to the lumbering first stage of a huge rocket. By the time this packet of protons leaves LINAC-2, it'll be travelling at 1/3 the speed of light. It's about to enter the booster, stage 2 of the rocket, if you will. In order to maximise the intensity of the beam, the packet is divided up into 4, one for each of the booster's rings. Straight acceleration is now impractical, and the booster is circular, 157 metres in circumference. In order to accelerate the packets, they are repeatedly circulated, and the electric field is now pulsed, in the same way that you push a child on a swing each time they reach a certain point. Magnets exert a force on the passing protons at right angles to their direction of motion, and so powerful electromagnets are used to bend the beam of protons round the circle. The booster accelerates the protons up to 91.6% of the speed of light and squeezes them closer together. Recombining the packet from the 4 rings, it's then flung on into the proton synchrotron, by analogy stage 3 of our rocket. Let's just follow 2 such proton packets. The proton synchrotron is 628 metres in circumference, and they circulate for 1.2 seconds, reaching over 99.9% of the velocity of light. It's here that the point of transition is reached, a point where the energy added to the protons by the pulsating electric field cannot translate into increased velocity, as they're already approaching the limiting speed of light. Instead, the added energy manifests itself as increasing mass of the protons. In short, the protons can't go faster, so they get heavier. The microscopic kinetic energy of each proton is measured in units called electron volts, and now the energy of each proton has risen to 25 giga-electron volts, or GeV. The protons are now 25 times heavier than they are at rest. The packets of protons are now channeled into stage 4, the superproton synchrotron, a huge ring 7 kilometers in circumference, designed specifically to accept protons at this energy and increase it to 450 GeV. Soon, the packets of protons will be energized sufficiently to be launched into the orbit of the gigantic Large Hadron Collider, or LHC, which lies between the Jura Mountains and the Alps, and straddles both France and Switzerland.
Is a stream of trillions of tiny particles. When the power is turned on, they accelerate from 0 to 60,000 miles per hour in a fraction of a second. Increase the power, and the particles go faster and faster, until they're whizzing around the tunnel at 11,000 times a second, which is almost the speed of light. But just like the train, they never quite reach that ultimate speed. They can only get to 99.99% of the limit. When that happens, they too start to travel in time. We know this because of some extremely short-lived particles called pi mesons. Ordinarily, they disintegrate after just 25 billion. Of a second. But when they are accelerated to near light speed, they last 30 times longer. These particles are real-life time travelers.
The Atlas detector is our tool for detecting the Higgs. It is situated at CERN in Geneva, Switzerland, and will be used to detect the high-energy collisions produced by the Large Hadron Collider. It measures 44 meters long, 25 meters in diameter, and weighs in at 7,000 tons. Two beams of protons will be accelerated in opposite directions close to the speed of light and collided at the center of Atlas. How do you create a massive particle such as the Higgs? Total energy of 7 tera electron volts. This, combined with the energy of the other proton traveling in the other direction, produces a collision with the energy of 14 tera electron volts. Upon a collision, all this energy becomes hundreds of different kinds of particles. It is in these conditions which, if it exists, the Higgs boson will be created by the LHC and detected by Atlas.
But Einstein never intended his wormhole as a tool for space travel. His wormhole is theoretically created at some moment of time. It opens up briefly, then pinches off. Anything that tries to pass through it will get crushed when it squeezes apart.
The ship would have to be big to carry a huge amount of fuel, enough to accelerate it to nearly the speed of light. Getting to just beneath the cosmic speed limit would require 6 whole years at full power.
T-minus 10 seconds.
acceleration would be gentle because the ship would be so big and heavy. But gradually it would pick up speed and soon would be covering massive distances. In just 1 week, it would have reached the outer planets, gas giants like Neptune.
But there are still many unanswered questions beyond the standard model.
Some of the things that Atlas could discover that are beyond the standard model are things like dark matter, supersymmetry, or even extra dimensions.